Hey everyone, welcome back to The Explainer. Today we're taking a complex topic, grounding it in the facts, and breaking it down so it actually makes sense. We are looking at something completely invisible, yet it absolutely rules our modern world. I'm talking about that invisible river of energy flowing through the walls around you right now. Your phone, your computer, basically everything. We are demystifying direct current, and by the time we're done today, we're going to take this from the abstract, subatomic level all the way to a tangy, hands-on DIY experiment using actual fruit.
All right, here's our roadmap. 1. What is direct current? 2. The math of moving electrons. 3. Tools of the trade. 4. Current and the body. And 5. The lemon battery. Let's dive in.
Starting off with Section 1, what is direct current? The invisible river.
So, to really wrap our heads around the tech we use every single day, we've got to zoom way in, down to the microscopic movement that makes all of our devices actually work. Direct current, or DC for short, is basically the flow of electrons in just one direction through a circuit. They're on a one-way trip, moving straight from the negative terminal of a power source right toward the positive terminal. And you know what's wild? This one-way street for electrical charge is the exact same fundamental concept that powered the very first batteries invented centuries ago. Now this is where it goes from total chaos to this beautiful, organized flow of power. Imagine a standard metal wire, like copper. The outer electrons of those metal atoms aren't really held very tightly to their nuclei. We call them free electrons, and honestly, in their natural state, they're just bouncing around completely randomly. It's totally chaotic. But the second you introduce an electrical energy source, like hooking up a battery, it acts like a traffic cop. It forces all of those chaotic free electrons to snap to attention and move in one uniform direction. That synchronized, aligned movement, that is exactly what creates direct current. And simply put, the more free electrons you have moving together, the greater your current.
Moving right along to Section 2, the math of moving electrons. Ampere's legacy. Okay, so we know what this flow is conceptually, but how on earth do we actually measure it? Well, for that, we owe a massive thank you to the French physicist André-Marie Ampère. Back in 1820, he was doing these groundbreaking experiments on direct currents in wires. 6.2 times 10 to the 18th power, over 6 billion. Let that sink in for a second. That is the exact number of individual electrons it takes to equal just one single coulomb of charge. Since Ampere was figuring out the intensity of this current, we measure it in his honor using the ampere, or A. When you have a current of just 1 ampere, it means one entire coulomb, again, over 6 billion electrons, is surging past a single microscopic point in a wire every single second. It's just a mind-boggling scale of movement, and it's happening completely unseen.
Now the really crucial point here is how we actually calculate this flow, and please, do not let the math intimidate you. Think of this equation as our master key. I stands for our electric current. It equals Q, which is the total amount of charge measured in those coulombs we just talked about, divided by delta T, which is just the time interval in seconds. It's really that simple. Current is just how much charge passes by over a given amount of time. 1 coulomb passing per second equals exactly 1 amp. Let's actually put this master key to work, all right? Say we've got a wire, and 0.85 coulombs of electrons are cruising past a point in exactly 2.5 minutes. Step 1, we identify what we know. Charge is 0.85 C, time is 2.5 minutes. Step 2 is super important. Our formula specifically requires seconds, so we convert that 2.5 minutes into 150 seconds. Step 3, we just plug those numbers right into Ampere's master key. Divide our charge of 0.85 by our 150 seconds, which brings us to step 4, giving us a final current of 0.0057 amperes. Boom. Just like that, we've successfully measured the invisible physical world.
All right, on to Section 3, tools of the trade, measuring the flow.
So we've conquered the whiteboard theory, right? But how does a real electrician actually measure this stuff out in the field safely? They use an essential tool called an ammeter. An ammeter is designed to determine the exact amount of electric current running through a circuit. It's basically the real-world tracker for our invisible river of electrons.
But here's the kicker. How you hook up this tool matters just as much as the tool itself. An ammeter absolutely must be connected in what's called a series circuit. Why? Well, because in a series, there's only one single path. Every single electron flowing through that wire is physically forced to go directly through the ammeter, which gives you a perfectly accurate reading. If you were to accidentally connect it in parallel, you've suddenly created multiple paths. the river splits. Some current goes into the circuit, some goes through the meter, and you end up with a totally inaccurate reading because you're literally not catching all the flow.
Which brings us to Section 4, current and the body, the high stakes. So we've been talking about copper wires and theoretical math, but what actually happens if this massive, invisible flow of energy takes a detour through human biology? Remember earlier when we said just 1 ampere is billions upon billions of electrons? Look at what tiny, fractional slivers of an ampere can do to a human body. At just 0.0008 amperes, you'll feel a slight tingling. Jump up to 0.064 amperes, which is still a tiny fraction, by the way, and it's painful, though thankfully you can still let go of the wires. But by the time you hit just 0.075 amperes, you are in severe pain and having difficulty breathing. And at just half an ampere, 0.50, you are facing possible heart fibrillation. It takes a terrifyingly small amount of current to be physically devastating.
And to make matters worse, this danger is compounded because all those moving electrons actually cause wires to heat up. Think about the electrical panel in your own home. Electricians are routinely working on household circuits rated for 15 amperes or even more. When just half an ampere can stop a heart and massive electron traffic jams can cause literal fires by heating up the wiring, well, it makes absolute sense why professionals always kill the power before doing their job.
Okay, let's lighten things up a bit for Section 5, the lemon battery. DIY power. Let's switch gears to something definitely less lethal and, honestly, a lot more fun. We can release some of that tension from the high-stakes biology and apply our newfound knowledge to a mini investigation you could literally do in your kitchen. We can actually generate real, measurable, direct current using a piece of fruit. Here's the science behind it. The natural acid inside a lemon acts as an electrolyte, basically a conducting solution. To capture the flow, we insert 2 conductors made of different materials to serve as our electrodes. A classic, surefire combination is using a zinc strip on one side and a copper strip on the other.
So how do we actually maximize this, lemon power? Well, we take that acid solution, our zinc, and our copper strips. Because the current is going to be incredibly small, we connect a highly sensitive ammeter. We're talking 1 set to the milliamp scale, and we connect a small load, like a tiny LED light. Now remember what we learned about series circuits a minute ago? If we take multiple lemons and link them all together in series, forcing those free electrons down one single path, we actually increase the push. If you were doing this right now, you'd literally see the current reading on the ammeter jump up, and your little LED light would glow noticeably brighter.
Which leaves us with a pretty fascinating question to wrap up today's explainer. Based on that tiny milliamp current from just a single lemon cell, could you link enough lemons together in series to safely power your entire house? It's a really fun thought experiment that challenges you to think about the absolute incredible scale of the direct current we rely on every single day. Hey, you've got the master key equation now, so maybe grab a calculator and imagine just how big that invisible river of electrons really has to be. Thank you so much for joining me today, and as always, keep exploring.